Welcome to the XPages Insights into Big Data using Parallel Multi-Database Searching project. With the dawning of big data and analytics, we as developers need to, more than ever, make sure that we efficiently utilize all of the computing resources that are available to us, that is both hardware and software, in order to make sure that our applications optimally harvest such big data. This project contains a sample application that demonstrates a couple of different things. Firstly, it demonstrates a data partitioning pattern to enable big data scalability, which can potentially run into terabytes of information. This is achieved via a custom managed bean routing layer within a dataless XPages dashboard application. Secondly, it demonstrates multi-database parallel searching across a large data set. Effectively, when a search is requested within the dashboard user interface, a multi-threaded concurrent search is carried out across all of the 26 different configured databases before providing a seamless search result back to the end user. This is achieved via a managed bean that executes multi-threaded search logic using a special abstract class implementation that allows the current user session to be shared across multiple threads within the XPages runtime for any given request. And the name of that abstract class, as we can see here, is the thread session executor, and we'll come to look at that in a few moments. The data model for this project has been partitioned into multiple NSFs. This partitioning has been driven by a normalization of the data based on company names and usernames. Central to this project is the XPages Insights.nsf application. This application contains only XPages application code. It does not contain any document data. So it effectively operates as a XPages front end or XPages dashboard application that consumes and manages data from the other normalized partitioned NSFs. In practice, there are two main data stores within this application data model. Firstly, the profile store. This contains 26 databases, which are normalized A through Z based on the company name. And programmatic access is carried out via first character of a company name. Secondly, there is the social store. Again, this contains 26 databases, normalized A through Z, and programmatic access is carried out via the first character of the username or email address when logging in. The social store is used to store things like a recently viewed profile list for each user, etc. I will now describe a couple of different scenarios for interacting with the XPages Insights application and the underlying data store. Firstly, in the case of interacting with the social store, when I log in as myself, obviously Tony McGuckin, T is deduced as the first character of my username. That means that the custom managed bean routing logic will route my request into the t.nsf social store application in order to retrieve my recently viewed list of company profiles for display on the Insights homepage. Likewise, when I continue then to interact with the application, such as viewing other company profiles, the corresponding social store t.nsf will be used to store my viewing events. Secondly, in the case of interacting with the profile store, if I choose to search for a company profile which may have the word Owen, O-W-E-N, within the name, O will be deduced as the first character of that search term. In turn, the custom managed bean routing logic will retrieve the O.nsf application from the profile store and use this to retrieve any matching company profiles. Now, in this case, the application is searching inside a single silo or a single application. But by using the XPages Insights application, I can choose to perform a global search, whereby the search will be scanned across multiple silos or multiple applications. Therefore, the global search will scan all 26 before returning a seamless list of search results. So let me now briefly show you some of the application features before I deep dive into some of the underlying code. So firstly, I will log in as myself, as we can see here, Tony McGuckin. And in this case, the first character T is deduced from my username. In turn, the custom managed bin routing layer has retrieved my recently viewed list, as we see here on the home page, from the t.nsf application. So these are company profiles that I have previously viewed on other occasions. And each time that I view a company profile, it will get listed into this recently viewed list in date descending order. Also seen here on the home page is a data view showing company profiles from all the different back-end databases, A through Z, as we can see here. And we can use this index to look at the different company profiles like so. And if I expand a company profile entry, here we have ability to see the abstract information, but to also open up the full profile. So in this case here, I can view the profile of the VBase group. And once again, by way of using the custom managed bin routing layer, this profile information is extracted from the V database. And of course, if I now revisit my home page, here I can see that my recently viewed list has been updated with the VBase group company profile at the top of the list. If I now select the Find a Company tab, I am presented with a type ahead, which will allow me to now start drilling down into the underlying data set. And again, this uses the custom routing logic whereby as I type, the first character is then used to extract the corresponding company profile information. So as you can see here, as I start to type, the type ahead filters out the matching results, allowing me to view the corresponding company profile like so. And more interestingly, if I just go back to the Find a Company tab and choose Advanced Search, I'm then presented with a couple of tabs which allow me to perform advanced searches. And this includes the option to perform, as we can see here, a global search. So the default is to search within a single silo based on first character of the company profile name or search term, and to also then have this secondary option whereby you can perform a global search across all of the data set. So let's just look at some examples. So if I were to type in the word Owen as described back in the slides and choose to perform a search, here we can see that it finds one entry. And this entry will have came from the o.nsf profile store application. Now let's do something different. Let's perform a global search for the same search term. And in this case, we can see that it finds 42 results across the entire backend data set. So in this case, the 26 databases indexed A through Z have all been searched and found exactly 42 results or instances of Owen, as we can see here. And of course, we can also provide other wildcard or single character search terms and so forth. As we can see here, if I put in 2 question marks denoting 2 single characters within this position and perform the same global search, we now find that it gives us 51 results across the entire data set. Or of course, we could use the wildcard characters as well. And in this particular instance, here we find the system giving us back 200 results. But of course, in this case, our max results have been set at 200. So let's toggle this up to all and perform the same search. And in this case, we have now got a result set containing 3,128 results. What is also interesting to note here is that the result set is presented to you as the end user in a seamless manner within this data view, as we can see here. And also notice that we can page through the result set easily using the standard pager, as we can see up here. And we can also toggle the sorting based on relevance order. And again, this is all managed inside the custom managed bean infrastructure. And as seen here, amongst the search results, if you look at the first characters for each of the results, you can see a blend of different alphabetic characters, such as C, U, E, and so forth, which gives you an indication of the origin of those particular entries relative to their back-end database. So as an end user, using this dashboard application, I am oblivious to the fact that there are 26 different applications in the background, and by way of the flexibility given to me as an XPages developer, I can still give the end user rich interface features such as paging and sorting and so forth. Also, just let me point out to you that all of the company names that are listed within this dataset are completely fictitious. If I choose here to go to the administration, dataset administration page, as you can see here, you will find options here to initialize the underlying dataset, or indeed reset the data or delete the data. And you also have control over the sample dataset size. In my particular case here on my machine, I have already initialized the data with 500,000 documents. That is to say that the 500,000 documents are initialized and dispersed across all of the different databases. So the 26 different NSFs within this data model have an equal distribution of the 500,000 documents. You should also take note of the test harnesses page, as we can see here. And if I click on the link, I'm then presented with an XPage which gives me links to other test harnesses. Now, this is a development technique that I use myself, whereby I create standalone test harness XPages which contain custom controls of interest that are used throughout the application. And what I try to do is isolate those custom controls into a test harness, whereby I can test those custom controls outside of the context of the actual XPage they are meant to be used on. Secondly, also notice the presence here of this Manage Debug Mode option. So what you can do here as a developer, you can turn on debug mode and use the test harnesses, or indeed use the application itself, and view rich server console output as you interact or test the application. So for example, if I turn on debug mode and click on apply here, we can see that by using the dump object that we are now in debug mode. Furthermore, if I just minimize my browser a little bit so we can see my Domino server console, you can also see the presence of the debug mode information as seen here. And again, this is nothing more than simple phase lifecycle listening code which emits system outs onto the server console. But the important point about this particular technique is that if I just come back into the application, and if I choose the test search bean, test harness, for example, what you can see here is an XPage that contains the exact same custom control used inside the application. That is to say, this part of the XPage we see here is indeed the same custom control used back on the application XPage, but here I have used it in isolation inside this test harness. And with debug mode turned on, what I can do is now start to test the custom control. So for example, if I choose Owen again as the search term and click on search, we can now see in the server console output information which tells us exactly what is happening as we process the request relative to the lifecycle execution. So for example, in this case, here we can see that the max docs is set at 200 Do search across silos, false, so it's just a single silo search. We have our search criteria, which is company name equals Owen, the first character being O, and then we start to see how the managed bean infrastructure is setting itself up in order to extract the relevant company profile information. And as you can see here, the managed bean infrastructure routes itself down into the O database and ultimately does the search to find one entry and so forth. Furthermore, if we come back into the test harness, again, if I choose global search in this particular case and choose search again, back on the server console, we can now see a different type of server console output. In the case of doing a global search, we are using multi-threading in order to perform the search concurrently across all databases in parallel. So for example, if I just reverse back up through the server console output, I come to a point where the request was started, as we can see here. So when I clicked on the search button, of course, the request went into the server and we started to invoke the application phase down here, which includes the custom search logic. So the search bean starts to do the search. It's performing the search across multiple silos. Again, the same search term is used, but in this particular instance, we can now see that the search bean is creating threads for each of the different silos. So for example, for the A database, as we can see here, inside the profile store, we have the A database. This is assigned a search thread, its own search thread based on key, which will go off and search that database in isolation of all the other threads that are happening at the same time against the other databases. And ultimately, as we traverse down through the console information, we can see that each of the different alphabetic keyed databases are assigned a search thread, and then ultimately each of the threads are asked to run themselves. So the start method is called on each thread, which then performs an asynchronous execution of each of the threads against each of their designated target databases. And this particular debug technique is also applicable, like I say, not just for the test harnesses, but also back inside the application itself. For example, if I go back to the Find a Company page, so for example, if I start to type in the letter O, as we can see here, immediately we can see on the server console output that we have the backend managed bean infrastructure starting to route my request. First off, it identifies the fact that I've typed in O as the first character, and then starts to perform a routing of the backend databases, ultimately into the O database, to find all entries beginning with O, which are then presented to us back inside the type ahead, as we can see here. So just to iterate that this is a particularly useful debug technique, which you can turn on and off for either development or production mode. So the most interesting aspects of the code within this application can be found inside the insights.nsf application itself. The profile store and social store applications contain no XPages design elements at all. They simply contain forms and views for the relevant document information. So if you open up the insights.nsf application inside Designer, you will find a number of XPages and of course a number of custom controls. Furthermore, if you look inside the code Java design elements, you will find a number of different Java class implementations. The most interesting of which is the search bean and also the data bean and profiles bean, which perform most of the data routing and also the multi-threaded searching capability. So let me just take a look at the search bean implementation in order to point out the most relevant parts which you can reuse yourself or indeed create your own implementation of a multi-threaded application. Inside the search bin, what you will find is a managed bin which extends the data bin, implements serializable, and provides an implementation for the iSearch engine interface. So in terms of extending the data bin, if I take a look here at the data bin, you can see that it provides a number of different methods which allow us to get and set different databases based on the company name or username key, but also to calculate the remote database paths and so forth for any given database. And the logic that has been implemented here on the data bin uses the faces config XML file heavily in order to provide the configuration for the different databases. So for example, if I open up the faces config XML file as we see here, you will see a number of different managed bins listed, such as the debug bin, profile bin, companies bin, and so forth. But if I traverse further down the XML file, here you can see the profiles being listed, and in its configuration it has managed properties for such things as the server name, and as you can see here it is an inline server-side JavaScript computed expression. But then it also has database name properties, one for each alphabetic character, denoting each of the different databases. So for example, for database underscore A, we have a path to the profile store A database and so forth. And again, if I just traverse down through the XML file, you'll also find a declaration for the social bin. And again, given that the social bin works with the social store, we have the same type of format. A server name managed property, and then relative database name properties for each of the alphabetic characters for each database, A, B, C, and so forth. So just going back then to the search bin, within this managed bin, you will find a number of nested classes. As you can see here, we have the search thread FTDB, and the search thread FTVW. And then there are associated methods which allow searching by either company name or by company name based on full text DB or full text view searching, along with other methods that perform the sorting by relevance order and so forth. So let's just take a look now at the search thread FTVW for one example. So search thread FTVW extends double-line thread, as we can see here. Furthermore, it provides a private member, which is an instance of the thread session executor. This is a special abstract class available within the XPages runtime since version 8.5.3. But ultimately what it does, it allows a thread to share a user session as it executes. So for example, here we can see that within search thread FTVW, the private member variable is constructed. And in this case, you can see that the run method implementation has indeed got a session parameter. This represents the current user session. So by using that session within the run method, we can then share the current user session inside the thread, or indeed any number of instances of this thread. This in turn allows my application here to use the current user session and perform multi-DB searching based on that session. And if I just move down through the code, you can see ultimately that as we pick up results in the search, those are added into an array list of search results. And note the fact that the search results array list is protected by a synchronized block, because the search results array list is defined as a member variable of the search bin itself. So this ensures protection against concurrent access by different threads trying to add results all at the same time into that array list. Furthermore, if I just move down through the code, here I can see that the that the implementation for the run method makes use then of the executor member variable in order to call its run method. And also note the presence then of another synchronized block here within the run method, which blocks the owning object. So in this case, the search bean is blocked until this search thread is finished searching. It will then notify the owner, or notify the search bean in this case, that it has finished searching, and therefore allowing the search bean to wait for all of the threads to perform their searches concurrently and ultimately deliver back a seamless search result after all of the threads have finished searching. Furthermore, if we take a look then at one of the company name search methods, so for example, if we look at search by company name FTVW, here we find the actual implementation of that method. So this is the actual method that is used back inside the test harness page that we looked at earlier. And ultimately, when this is executed, we can see that if we are performing a multiple DB search or a search across silos, as we can see here, inside this if statement, there is then a number of search threads created and put into a search threads map. This is a step one in that a search thread is created for each of the data provider databases. So coming from the faces config XML file, each of the databases is then assigned its own search thread. And then as a step two in this process, each of the threads are asked to start themselves. So here we can see that the for loop iterates through the search threads map and asks each of the search threads to start themselves. Note that this is not a call on run, for example. It's a call on start, which is important. This allows this owning search bean thread to start the corresponding search thread without having to wait on it. And as a final step, the owning search bean now waits in this third step for each of the search threads to notify the owning search bean that they are finished. Hence, we have another synchronized block here, as we can see, that is blocking this. So in this case, this being the owner of each of the search threads, and it will wait until each search thread is finished. And ultimately, when it is finished, the search results array list will contain a seamless set of results representing all of the results accumulated by all of the search threads. And what's interesting here is that we can also test this inside Designer. If I choose to go into debug mode and change my perspective to the debug perspective, in this case, I already have set a breakpoint on the run method of the search thread FTVW. And if I go to the application, and if I were to, for example, go to the advanced search page and perform a search for Owen again, using a global search in order to invoke the multi-threading. When I click on search, as you can see here, the breakpoint is executed. And of course, as you can see here, each of the search threads have been suspended within the Domino server. So we have all of our different search threads that have been spawned and asked to start themselves, now suspended within the run method, given that we have set a breakpoint. So here we have the A thread, the B thread, and so forth. So this allows me to also debug my multi-threaded application inside Domino Designer. Given that we are now creating a multi-threaded application, you may find it useful to also be able to analyze the activity of threads and monitors within your application. So by using the Domino Server console, if I were to create a Java heap dump, I will then be able to analyze activity of threads and monitors within my application. So for example, here on the server console, I issue the command tell http xsb java dump. That creates a corresponding Java dump. And if I then use a tool such as the thread and monitor dump analyzer, I can then open up the corresponding Java dump file, and then check on the thread detail within the runtime. And in this particular instance, here I can see that I have all of the different threads of interest that have been blocked, waiting on a condition on line 429 of the search bin Java file. And I can also see that my Domino server itself is blocked. It's waiting on my search bin request to complete. One other important area to consider when working with big data is to effectively manage memory, because big data applications can be extremely intensive upon both CPU and memory usage. So as a final example, let's just take a look at memory usage of this particular application using this multi-threaded concurrent searching ability. So previously we had done a search for Owen across the entire data set, which turned up exactly 42 results, as we can see here. Now what's interesting about that, if I, again, using my Domino server console, issue the command to create a heap dump. Now this is slightly different than a Java dump. In this case, we're creating a snapshot of the JVM memory heap space. And once again, I'm going to use a third-party tool to analyze the heap dump file and see exactly what's happening inside this application in terms of storing and managing those search results within the JVM heap space. So in this particular instance, I'm going to use the Eclipse Memory Analyzer. And I proceed now to open up the newly generated heap dump. And the Eclipse Memory Analyzer will now analyze the file because it's not human readable and present me with different ways of looking at the pertinent information. So after having analyzed the file, I'm now presented with a report which tells me about any possible leak suspects, that is, any very high consumers of JVM memory heap space, or indeed JVM memory leaks themselves. And if I just scroll down, here I can see a pie chart showing me the main suspects, one of which is problem suspect 1, as we can see here. But I can immediately recognize that there's nothing untoward happening here in terms of memory usage from the application itself. I can also use an object query language statement to see exactly what's happening inside our search bin. I can issue a select statement which will give me back memory insight into the search bin itself. And as you can see here, using the type ahead facilities within the editor, I can see all the different bins that are listed within my Insights application. So in this case, we're interested in the search bin. And let's just go ahead and execute that query. And from this window, I can now start to drill down into the information held within the actual search bin itself. So first off, I can see that it contains a list data model that represents the data model that uses the wrapped data coming from this array list. This array list is in actual fact the search results array list. And if I just drill into that object, what I can see is that it holds 41 instances of this JSON Java object. And again, if we just look back inside the application itself, we do indeed have, as we can see here, 42 results. And of course, given that back inside the memory analyzer, the indexing is zero-based, we do indeed have 42 instances of this JSON Java object. Now, what's more interesting then is the fact that it uses an amount of memory space. As we can see here, the shallow heap versus the retained heap figures indicate that the array list of search results is consuming 432 bytes of shallow heap space. But there is indeed a retained heap, a total retained heap of 117,000 bytes. So effectively that retained heap is all of the child elements that are represented as the JSON Java objects. So for example, just to reconfirm that, as you can see here inside the retained heap for that array list, we do indeed have 42 instances of the JSON Java object representing our search results. Now in this particular case, the memory usage is not very concerning, but let's go back to our application and execute a different search query, reanalyze another heap dump. And now let's just go back to our application and Domino Server console. So in this instance, what I'm going to do is issue a different query. Let's put in something a little more random and change over the max results to all in this case, whilst doing a global search. So having just completed the search, we can now see that we have a total of over 12,000 results for this fairly random search query, doing a global search. So of course now let's go back to our Domino Server console and generate a new heap dump. Once again then, using our Eclipse Memory Analyzer, let's go and open up the newly generated heap dump. And in this instance, we now have a different set of results, given that we have issued a different search query. So in this case, the leak suspect report tells me that there is exactly 31.7 megabyte being used by this NSF component module. So let's drill down deeper into this particular information. Let's take this class name and use that to, again, select all of the memory information from that particular object. So immediately here we can see that the shallow heap is quite small, but the retained heap size does indeed reflect the 30 odd meg of memory being used. And again, let me just drill down into the different objects within the NSF component module. And I can see here that there is a hash map contained within the object, and if I just drill down into that, I can see that this will indeed represent my user session. And as I drill into the information, what I will find is that I will come across my Java search bean along with the search results and so forth being held inside my view scope and ultimately consuming a lot more memory given the new search term that we had issued. So we can see in this case that the search bean is indeed the object that is consuming the most amount of memory for this particular heap dump. And again, if I expand out the details, here we can see the same array list representing the in-memory search results. And again, in this case, we have quite a number of the JSON Java object instances held within that array list. And once again, if I were to choose the array list and select Show Retain Set, again, of course, we can see then that we have indeed got 12,083 instances of that particular object, which of course is in line with the number of search results that we have seen here inside the application itself. So the point that I wanted to make was really that you should consider all things in terms of memory usage, CPU usage, and so forth when working with big data. And this particular application demonstrates some of the key aspects that you will encounter when working with big data, such as a partitioned data set and the sometimes uniquely odd requests or expectations from an end user in terms of querying and the demands that that puts upon your system. And as described at the beginning of this video, we as developers must now more than ever really consider usage of all computing resources available to us and find a balance between available resources, particularly CPU and memory usage, versus the potential number of users and concurrency that may happen between those, versus the functional requirements of a given application.